So let's consider a hyperbola given by the equation x squared over a squared minus y squared over b squared equals 1, where a and b are positive real numbers here. I've already sketched the graph over here. The green curve represents the hyperbola, so this is our hyperbola. Again, x squared over a squared minus y squared over b squared equals 1. That's the hyperbola. And we want to identify a couple of features of this hyperbola, namely the foci. Remember, foci is the plural of focus. The vertices. So the vertices are where the hyperbola crosses, in this case, the x-axis, because we have x squared minus y squared. Remember, if we reverse the x and the y, this hyperbola would cross the y-axis. And then the asymptotes. So what happens to this hyperbola as x gets very large? Those are the questions we want to ask. So let's start with the foci. For the foci, there's a nice relationship between these constants a and b and the coordinates of the foci. We're not going to work this out in these notes, but you can derive this very similar to how we did for the ellipse. It turns out that the foci have coordinates. We can see just by looking at this picture that the foci live on the x-axis, and the foci have coordinates f1 is equal to c0 then, lives on the x-axis, and f2 is going to be negative c0. By symmetry, it's just a reflection over the y-axis. And the question here, obviously, is what is c? And this is the portion that you can feel free to derive yourself, or you can find a video online, or just get a hold of me personally and we can work it out. But the formula for the coordinate of the focus or foci of a hyperbola is this, that c squared is equal to a squared plus b squared. Remember, for the ellipse, it was a squared minus b squared. We drew a triangle and worked this out. A similar argument will give you this for the hyperbola. And so there's the coordinates of our foci. The next question is, what are the vertices? So the vertices also lie on the x-axis, but these lie on the curve itself. So the vertices are the points on the curve for which y is equal to 0. The y coordinate is 0 when your points live on the x-axis. And so for this, we just plug into the formula itself and solve for x. Okay, so again, v1 and v2 lie on the x-axis. In this example, if everything is switched around, then the vertices would live on the y-axis and x would be 0. But we just plug in. What we end up with is that x squared over a squared minus 0 has to equal 1. This, of course, implies that x squared is equal to a squared, and therefore x is equal to plus or minus a. And the positive a, that's going to correspond to v1. Negative a, that's going to correspond to v2. Remember, a was already assumed to be positive in our assumptions. So our vertices are v1, coordinates are for v1 are a comma 0, and v2 coordinates are negative a comma 0. Okay, so those are the foci and the vertices. The question now is, what's the an equation for these any of these asymptotes? This looks like two asymptotes here. And let's just focus on the case when x and y are both positive, and then we can try to ask what happens after that. If anything different changes, but maybe not. So let's go to the next page so we have some room to work here, but we're going to, again, focus on this first quadrant asymptote when x and y are both positive and x gets very large. Remember, our equation for the ellipse, or the hyperbola, sorry, is x squared over a squared minus y squared over b squared equals 1. And again, we're going to assume that x and y are both positive, and then we're going to consider what happens as x approaches positive infinity. This is the question. What happens to y, of course? So is there a bound? What's going on? So the first thing we should do, if we want to try to find a limit in terms of x, but that tells us something about y, is we should solve this for y. Solve this equation for y, and this is where our assumptions are going to come in, because there's a lot of squares here. I mean, the a and the b squared can stay, but the y squared and x squared we have to deal with. So when we solve for y, we end up with y squared over b squared is equal to x squared over a squared minus 1. We multiply through to get that y squared is equal to b squared over a squared times x squared minus b squared. And then we take a square root, and again, this is where we know that everything is positive. So, well, we have assumed that everything is positive. So y is now equal to the positive b can be factored out of the whole thing, and then x over a. We probably should, maybe what we should do is combine like terms here, but this is okay. X over a squared minus 1, x squared over a squared minus 1. And so here's the idea. If we're taking a limit as x approaches positive infinity, then as x gets very large, this term gets very large. But the negative 1 is obviously a constant, so that is going to, as x gets very, very large, we're being kind of loose here with the limits, but as x gets very large, this term right here, this minus 1, this becomes negligible. As x gets really big. And so what we end up with is that y is approximately equal to b times the square root of x squared over a squared, again as x is very large, for very large x. And now we can just reduce the square root, and so this is equal to b over a times x. And so what that tells us is that this line, this red line that we made very bold in the first quadrant, is equal to the equation of this line. Here is y is equal to b over a times x. That continues into quadrant 3 with the same formula. So that line continues over here in quadrant 3 with the same formula. But these other lines, if we make some other choices for maybe x and y, just x negative, just y negative, the equation of this line is going to be y equals negative b over a times x. And so what we can deduce here is that these two asymptotes, depending on which arm of the hyperbola you're on, the two asymptotes have equations y equals plus or minus b over a times x. So this is an equation of the asymptotes of our hyperbola.